right, Alan, do you mind presenting our presenter?
Sure. Everyone, it's my pleasure to introduce today's speaker, Henrik Barojo. He is currently a robotics lead for a robotics company called All3, and he also worked in Ocado, another lead robotics company, for several years. He holds a PhD in robotics from the University of Edinburgh, doing motion planning and trajectory optimization, and he has also been the lead developer of Julia Robotics. So please, everyone, join me to thank today's speaker, Henrik, for coming to speak to us.
All right, thank you so much, guys. Thank you very much for the introduction. I think that's the first time I got such an introduction, and thank you for Andrew for helping organize this. I just realized I'm not sharing the actual slides. Okay. Let me also try to pin you guys. Okay, this way I can see you guys better. So, just a small correction, if I can. I'm just a contributor for some of the Julia robotics stuff, so I'm not the lead contributor. Just a small correction. Okay. Yeah, my name is Henrik. I will be talking about trajectory optimization with whole body dynamics today. My goal is to have like quite chill presentation because it's a bit late in the UK. It's 7 p.m. on a Friday, so I'm not at the pub as but it's a great pleasure to be here. Don't get me wrong. So I'm really happy to be here and talking to you guys, and I can't wait to hear the questions that you have, and hopefully we can have some nice discussions. So I mean, the pictures on this slide are just a small motivator for what we're about to talk through. You can see the space shuttle re-entering Earth's atmosphere. You can see SpaceX launchers doing the re-entry maneuver and landing on the launch pad. And you can see the Boston Dynamics Atlas performing probably one of the most famous robots doing very dynamic maneuvers. And what all of these have in common is that they are solving optimal control problems. And so what I'm going to be talking about, like the optimal control problem and this framework of seeing the world around us and being able to solve these kind of problems with very concrete and useful applications, to me is one of the most fascinating things that I had the privilege to study and do research on during my PhD. And there are many ways of solving these problems, obviously, and I will only speak about one, which is my favorite method. But yeah, hopefully you will enjoy it. But before that, I think I will give a bit of an introduction and speak a bit about me. So you guys get to know a bit more about my background before we dive into the technical details. So I started doing robotics in about 2016. And this is when I went I'm originally from Portugal, but I went on an exchange program to Edinburgh, the University of Edinburgh, for my master's. I spent some time there. And then I applied and managed to get an offer for doing the PhD there. So that's where I stayed from 2017 to 2021. And here in this picture, you can see some of the robots that I used and I did experiments on during and throughout my PhD. You can see the quadruped is Animal from Anibotics is Animal B. And on top of it, we had mounted the Kinova arm, which is from Kinova is in Canada. And these robots are not made to be put on together, but they're running different controllers. But it was a nice way. At the time, you couldn't just simply buy a local manipulation platform as a quadruped and arm already off the shelf. So that's why we made our own. You can also see this humanoid. The white humanoid here is NASA's Valkyrie robot. Is a very nice and very complicated robot. And here you can see walking over uneven terrain and doing some local manipulation task. And then you can also see Taos performing a very small jump. I will show a video of this later. This humanoid is from PAL Robotics, and they're based in Barcelona. After my time in academia, I switched to industry, and I worked for around 2.5 years at a company called Ocado. I'm not sure if you guys have heard about them, but they have big contracts with big supermarket chains like Sobeys or Kroger's in US and Canada. And you can see here on the picture in the left, basically they have huge warehouses with lots of groceries inside. And you can see that this is on the left here is called the hive. You have like thousands of mobile robots. They're quite big. It may not look like in this picture, but they're quite big. And they're going around very fast on these tracks, so they can go back and forth, left and right, and go close to each other by only a few millimeters. And under all of them, under all the tracks, you can see the white totes. These are like plastic boxes containing stock, and they are stacked up very high, like a few meters, and they can go up, I think, to 20 something totes stacked. And so the idea is that you keep the very popular items that you're selling at the top, because otherwise the robots have to go use one of the robots to take the one on top of the stack, use another one to retrieve the one underneath that, and so on. But it's a very there's lots of optimization going on as well, and lots of route planning is very interesting. However, I was not working on that. I was working on the packing stations. So you can see here on the picture in the right a UR10 robot arm with a suction cup as the tool for picking the items up. And you can see that the white totes that have only one kind of item, those are the stock. But you can see here this one on the towards the left that has a red container inside, and that one has plastic bags. And this is where you pack the item. So that's going to the customer. It's going to get on a van and delivered to the customer. And so the job for this kind of robot is to look at the stock tote, which can be completely chaotic and has many different kinds of items. Some are rigid, some are soft, some are fragile, some are not fragile. And so you need to pick the easiest one to reach it and be able to then pack it neatly in the customer's bag. So like very interesting problems here from engineering and research point of view. And most recently, actually, I've been here for a bit over a year now. I am at a company called All3, also based in the UK, in London. And this is our robot. So All3 is a construction company. And what we are doing in the robotics department is, on the mobile robotics department, is developing this platform that can walk around the construction site and help with many of the tasks. And we are not doing regular construction with concrete. There is a concrete core for the elevator shafts, for the stairwell, but actually we're focusing on renewable sources and more environment-friendly materials. And so we're using actually CLT, which stands for cross-laminate timber. And it's not very easy to see, but on the picture on the left, if you see the blurred background, that is the timber. And yeah, so the picture on the left is showing a prototype, an early engineering prototype of the screwing tool that we use for driving these special screws that are very long to secure floor slabs, to secure wall elements. And yeah, the picture on the right shows the full platform that is modular. So you can switch the arm that is mounted on top of it. You can also switch the tool that is assembled, that is mounted on the tip of the end effector of the robot arm. But it's a pretty powerful robot, and is an amazing platform. So each motor on the legs, it can do a peak torque of 500 Newton meter. And the quadruped base itself is around 100 kilos, and it has a total payload of around 200 kilos. So it's a very impressive platform.
Is it deployed in practice already? I mean, is it on project?
Not yet. The company, so 1 year ago, nothing of this existed, and we're doing it all from scratch. So as you can imagine, it's still pretty early days. But yeah, we're working towards that. And in the lab in London, we have like a mock-up of the real construction environment where we're running tests. But soon we should be able to go to a real construction site and do preliminary tasks.
And they want to do that for what reason? Is it for, security reason, safety reason, or is it just because they're more effective than workers?
I would say both. So in such timber buildings, you just to secure the floor slabs, because these are prefabricated elements that get manufactured in a factory and then all put in a truck or multiple trucks and then get shipped out on site. And so there's lots of connections that you must make to secure the wall elements to each other or the floor slabs to each other. And so there's like thousands of screws that you need to screw on a single floor, which is very tedious, repetitive work. And usually people who do this, after a while, they tend to get a bit sloppy, to be honest. And so the fact that the robots don't get tired and the ability of being able to do repetitive, accurate work is one of the advantages. The other advantage is that obviously when the robot becomes capable of doing tasks other than screwing, more elaborate tasks, like for example, when the crane is lowering elements onto the building, these are quite dangerous. And if you look at how people currently do it, they literally stand under these very heavy prefabricated elements with hooks or using ropes to try and bring it to the place where they want to lower it. And it's quite dangerous, and especially if there's wind and the weather is not great. And yeah, robots can also, provided that there are no constructions taking place in very busy city centers where there's noise regulations, you could in theory have the robots going around 24/7. Okay, that pretty much covers the work that I've done in robotics on a professional level, but I really like robotics, and I do have a few small projects that I spend some of my free time on. You can see here on the picture, on the weekend in my pajamas with our dog, Hercules, and what I wanted to show in this picture is the two very affordable standard open arms. You can just 3D print this at home and buy the servos, so each arm costs around $100, $120. That's what I did. I was experimenting with the Hugging Faces robot for the VLA. So I just trained with a few demonstrations using this kind of leader arm. You can grab it from the handle, and then this is the follower arm. And you can collect a few demonstrations and very quickly get something that generalizes really well. It's very interesting, and I recommend as a starting platform for exploration. This is just like a rotary inverted pendulum that I also was working on. And the reason why I work on these projects is because up until my PhD and postdoc, I was doing mostly software engineering and research using software. But I wanted, like, what kind of roboticist am I if I'm not able to design my own mechanical parts, do some sort of basic electronics? And so that's the motivating factor behind these projects. And here you can see a recent one, which is a three-legged robot with the things in white are PVC pipes, £3 on the hardware shop, and the blue things and red thing is 3D printed on my Bamboo Lab A1 Mini, which is also again a 3D printed that's really good for £150. So things have gotten really accessible, and you know, it's super cool to be able to do this kind of robotics work nowadays. Moving on to the actual presentation. So that concludes a bit the introduction about myself. I will show you this video, which is a video from the very close to the end of my PhD, and I'm quite proud of the whole sequence, because there's no cuts in this video. And I will let the video play and I will speak a bit over it. So it's the animal quadruped with the arm. And we start close to an object that we are interested in manipulating. In this case, it's a valve. And I will try to get my mouse off of the video so you can see the annotations below. So you can see the operation mode is switching between teleoperated and autonomous. So when I'm teleoperating, I'm only teleoperating it for walking with a joystick. And then I joystick it around, teleoperate it to walk close to an object of interest. And then I switched it to autonomous mode. And it's not completely autonomous because it still requires someone to tell it what it should do, right? In this case, when I was in front of the lever, I had to literally press the button to, okay, pull the lever. But yeah, you can see that here when I'm walking around the lab environment and now up the ramp, it's still using the the walking controller that Anipotics provides when you buy these robots. But then here again, in front of the gate, there are some reflective markers for the motion capture system. So we know the state of the robot, we know the joint positions, we know the position of the gate, and we kind of know the primitives for opening a gate. So we can just click the button, open gate, and what happens autonomously is the motion planning. We're solving the optimal control for optimizing the trajectory that we sent for the robot to execute. And that is considering the whole body of the robot. So the trajectory that it comprises not only the legs, but also the arm. Even again, they are two different robots made from different companies, and they are running two different controllers. But the trajectory is planned taking into account the whole body of the robot. So we're reasoning about joint positions, velocities, joint torques, contact forces, and the timing when we make or break contact, even though that is a predefined sequence. And here in the last task, you can see the robot reaches out for a handle, which is connected to a rope, which is in turn is connected to a bucket with unknown weight. I think it was like maybe 1 or 2 kilos. And the robot doesn't know about this weight. It just knows that it needs to pull the rope, and so the bucket weight acts as disturbance, and it has to plan this complicated trajectory. I will just go back and play it again, where it has to move the arm simultaneously and take steps. So this is a simultaneous locomotion and manipulation. The reason why the walking is a bit wonky is because of the disturbance of the force, the weight of the bucket. And then in the next video, here.
Can we ask one question?
Yeah, go for
I
it.
think you kind of answered it, but when you do press the autonomous button and then you're doing a task, so the task isn't hard coded, but the like it's going to solve a trajectory optimization problem, but that's hard coded, right?
So it knows the tasks. So what we hard code here is the knowledge of these kind of task primitives, like turning the wheel, pulling the lever, opening the gate. But every time it faces one of these tasks and you tell it, okay, you need to open the gate, it's able to, on the spot, plan the trajectory based on the robot's current configuration within the environment. And that's not hard-coded. So it solves the constraints for the problem are hard-coded, right? We know that there are contact forces involved, and we know that we know the dynamics of the robot, but those are constraints in an optimization problem that gets solved when you press that button.
Yeah.
So are these what you call the primitives? These constraints, hard-coded constraints?
Yeah, kind of. Yeah, those are things that I just have a function that creates an optimization problem for a lever, for a wheel, for a gate, and for pulling the bucket.
And do you use the image to figure out the position of the target states that you want to arrive at?
No, that's one way of doing things, but in this kind of demonstration, I was just using the reflective markers from the motion capture system. These reflective markers, you have like lots of infrared cameras around the lab, and if you attach like reflective markers on the robot and on the objects that the robot needs to interact with, you can get the state of these things in the world.
Oh, nice. Okay.
So it's a way to cheat perception. If you're not working in perception actively, and it was the case in my PhD, I was not actively doing research in perception, but I wanted to know the state of the environment, and I wanted to know the state of the floating base of the robot in the world, and that's why I used the motion capture system. So here in the next video, you can see a robustness test. So I'll just play through it. Let me mute it. And this was a reliability test where I'm basically adding some delta, random delta to the base pose, using the Anipotics controller to walk to that random place in the world. And then from there, I'm always calling the function that solves rotate the wheel task, okay? And what I'm basically showing here is that it doesn't matter where the robot is with respect to the wheel. As long as it is sufficiently close to the wheel, it is able to plan a trajectory that moves the whole body of the robot. So you can see that the robot is using its whole body, including the legs, to rotate the wheel. It's not just like moving the quadruped, then pretending that it's a fixed base robot arm only to rotate the wheel. And
So
the reason why...
Are you doing that to actually understand the force that the robot can apply, or?
Yes, so the reason why it's moving the legs into this configuration is to maximize the robustness to unexpected disturbances. And yeah, and also because some tasks do require taking steps, like pulling the rope to lift the bucket. This requires taking steps, so you couldn't just assume that the arm is a fixed base.
Hey, Hiki, can I ask one question? Sorry. Do you, in between, when you decide, you click the button to turn the lever, do you replan throughout the trajectory? Like you start and then you replan because for some reason you had some noise in the actuators?
Do you mean like as the robot is rotating the wheel?
Yeah.
Yeah.
No. So this would be a very nice next step.
This is a single plan for the whole thing.
Yes, exactly. So this is one of the...
And what is the fidelity of the plan? Is it discrete or is it a continuous plan?
It's discretized in time at a certain frequency, and it considers the full body dynamics of the robot. So I think we can talk about this in the discussion. It's a very nice point. But basically, what's happening is that when the robot is facing the wheel and I ask it to turn the wheel, on the spot, it solves an optimization problem considering the full body dynamics of the robot. And then it sends the uses the optimal torques from the optimization problem, uses those as feed-forward torques. And because we also know the positions and the velocity references, we use them as PD references with small gains. And you can see that the robot is able to track that quite well. And I even did jumping, so quite dynamic tasks, which you would think, and many people, when they spoke to me, they said they didn't believe this could be possible because you're just planning in one go and then executing it without replanning as you're going.
Yeah.
But because we're considering the whole body dynamics of the system, it is actually able to do quite good job at getting a good reference trajectory that we can then track using a relatively simple controller. So the controller is just a feed-forward torques plus small PD on reference positions and velocities. There's no quadratic problem being solved to track the whole body motion.
So are you going to show the math behind this at some point?
Yeah, that's what the presentation will be about.
Are you also always guaranteed that when you have a task like this, there is a feasible way to do it, given the flexibility of the robot?
If the task is not feasible, the solver will not converge and report an optimization error, saying, for example, feasible converge to an infeasible point, or it thinks that maybe the constraints are not, there are conflicting constraints. So the solver is smart enough to report those. Okay. So we reached the point where I'll go over the agenda briefly. So why consider dynamics? This is the next slide. Then I'm going to be talking about trajectory optimization. What is the trajectory optimization problem? And then I'm going to speak about direct transcription, which again, there's multiple ways of solving trajectory optimization problems, but this is the one I use and I like the most because of its simplicity. Then I will explain an important component for direct transcription, which are the dynamics defects. Then we will go through a small demo of a Julia package for optimization of trajectories for robot arms. So I will not be showing the quadruped stuff, only for fixed base robot arms. And then we will, I will have a slide with some pros and cons. And I will briefly mention a few packages from the Julia ecosystem. And that's it, then we wrap up. So why would we consider dynamics in the first place? So if I have two examples here, one on the left is a traditional assembly line of a auto manufacturer, and on the right I have the system that I was showing in the previous video, which is from the University of Edinburgh, the research platform where you have the quadruped and the robot arm mounted on it. And if you look on the left, basically, these industrial arms are quite powerful. They have large torque budgets. They're in a somewhat controlled environment, right? There's cages around. The interactions with humans are restricted, and the chances that there will be something unexpectedly pushing one of these robot arms are low, very low. And even if they do, they have so much torque available to them that they can easily neglect it. They can easily continue their stiff operation, and just with disregard for unexpected disturbances. And they are bolted to the floor, so there's no active balancing involved. But on the right, what we want to use these robot platforms for, so these mobile robots with manipulation capabilities, they have a limited torque budget. So they usually already require some active torque just to stand and to stay balanced. They are subject to external disturbances, so maybe another robot unexpectedly collides with them, or a person collides with them, or something else pushes them, or maybe they're just picking something up with more weight than they thought, than the robot would assume the object weighs. And we want to be able to execute many different tasks instead of a single repetitive task, and we need to be actively balancing. So these are very big differences from one scenario to the other. And I believe that we need to consider dynamics because of this. Like, we need to consider the full body dynamics of the robot. And we need to reason about the contact forces, the friction between the feet of the robot and the environment, and the torque that is available to the motors, not only for doing the task in a nominal condition, but also to think about how can we pick the best trajectory that maximizes the amount of torque that is left over, so I can use that leftover torque to compensate for disturbances. That was basically what my PhD was about thinking about on redundant robots, because you have the null space. How can you pick, and there's an infinite number of using that null space to come up with trajectories to solve the same task. How do you pick the best ones so that you have the most leftover torque available? Or you select the contacts carefully so that the contact forces lie as close as possible to the center of the friction cone to avoid slipping. And that's why I believe we should consider dynamics. But just a note that I found recently, last week, a very recent work that I have included it in the final slide, which maybe just throws all of this away, and but it will be a contention point for the discussion. Okay, so now that I have somewhat convinced you that it's important to think about whole body dynamics, let's first understand, well, I guess most of you already know this, so I'll be quick. What is the trajectory optimization problem? We have state, controls, and dynamics. If we are solving the optimal, we can solve this for robots, for landing boosters from rockets. We can do it for many things, but I will use the robotics context for explaining the optimization problem. For example, this robot arm has 6 motors, so it's fully actuated robot with with 1 motor per articulated joint. And so the position of each motor, as well as its current velocity in time at a specific point in time, that would be the state, right? That's X here. So Q is the vector of joint positions, 6 positions for this robot arm. V would be the vector of 6 joint velocities at a specific point in time. and X would be basically the concatenation of these, which give us the state of the robot. What are the current controls that we can command to the robot? Well, that's just the torque that we can send to the motors, right? That's how we change the state of the robot. And that's what this tau represents. The reason why I have this lambda here is that you can also change the state of the robot if you apply a force to it, right? If you go there and push the robot, that's another way to move the robot. But maybe let's ignore that for now. Let's assume that nobody's going to go there and apply a force to the robot. And so the way we move the robot is by passing current through the motors to apply torque at the joints. And that's our U, control.
What is the current really doing at the end? So is the angle of everything, or you can, what is the motor going to really do in terms of the various positions of the various legs and things like that? Can you go into the details of that?
Sorry, I didn't quite get the question.
Yeah, so I think you're saying that kind of the controls are the motor and you send some signals to the motor. But what does it do to the various pieces? What is the instruction that a motor is? What does it do really? Can you specify a position of everything? What do you really specify?
At the lowest level, the motors accept current, right? And when you provide more current to them, they spin in one direction or the other. And inside these motors, like they have, robot actuators are mostly a brushless DC motor attached to a gearbox. They can be planetary gearboxes.
So you have multiple motors. You have multiple ones. That's what you're saying.
The what?
You have multiple motors?
Yeah.
Okay. And how do you make sure that they just don't go crazy and go into a completely wrong direction?
So you would have a controller. So basically you have a controller controlling all the motors, where for this kind of controller, you would provide a reference for the motors. And you can control them usually in position mode, velocity mode, or torque or pure torque mode. And the way that I've been controlling, for example, the quadruped, like the animal and the Kinova arm, is you provide a feed-forward torque. So the way you calculate is in torque mode. Basically, you send a pure torque command to each motor, but the way that pure torque is calculated is with the feed-forward torques that are optimally calculated from the trajectory optimization problem, plus feedback term on the reference positions and velocities. And that's how you make sure that for every step in time, you are trying to track a trajectory as best as possible.
So you move from the trajectory to the instruction to the motors. That's the way to phrase it.
Yeah.
Sorry, can I add one question on this? Do you also control the feedback? Can you change this the PD controller that you have on the feedback?
Absolutely. So if you change the PD gains, basically you're changing is like a spring damper system, and by changing the gains, you're either saying that okay, you're putting more emphasis, for example, on tracking the positions very well, and then you have a very stiff system. Or if you increase the D gain a lot, you're increasing the damping behavior of the system, and so you're trying to track the velocities with more emphasis. But the goal, if you have quasi-direct drives, which are robot actuators with low gear reduction ratios, so say for example 1:8, you have a somewhat transparent actuation system, and what people want ideally is to keep the P and D gains quite low and to use the feed-forward torques as the main way of controlling the robot. And this is when you get some compliant behavior, and where you can go there and the robot is still doing what it should do, but it's not like a stiff table, or you can still move it, and it's a bit compliant. Okay, so we know the state of the robot, we know how to move it, and finally here, this bit, can you see my mouse when I'm hovering around the slides? Yeah. So this last bit here that we need is the last ingredient on the recipe is basically an equation that relates the states with the controls, right? So we can move the robot, but okay, if I control it somehow, how does it affect the state? How does the state change exactly if I send 5 Newton meter for one motor or 10 Newton meter for another robot? And this is what this equation of motion gives us. And this is for the full dynamics of the system. So you have the mass matrix here in the first term multiplied by which is a function of the joint positions, multiplied by the accelerations, and plus this H term here, which are basically the dynamics effects of the system, like Coriolis forces, centrifugal forces, gravity, acceleration. This is the term that accounts for those. And then on the right side of this equation, you have these torques that you send to the robot joints, plus the lambdas, which are the contact forces that you also use to affect the system. This Jacobian is just a Jacobian that relates the velocities applied at different points of the kinematic chain to joint velocities. And this S matrix here is basically a selection matrix because on underactuated systems like the quadruped, the base is floating. You do not have direct control over it. So it's just an identity matrix, but with a few zeros in there on the major diagonal to ignore, so that we don't send torques to the floating base, because we cannot do that. So state controls and the dynamics of the system. If you have all these three ingredients, it doesn't matter if you're talking about a robot, it doesn't matter if you're talking about a spaceship, or maybe a car doing autonomous racing, you have the tools to use this optimal control framework and solve trajectory optimization problems. And that is, again, as I said, one of the most fascinating things that I learned during the PhD, because you can use it for so many different things and is super, super powerful. Okay, what is the problem then? The problem is you have an initial state, right? The robot is in one configuration, and you want to move the robot to a different configuration. And you know this, how the system moves, you have the system dynamics. And so the goal is to find a control trajectory as a function of time, right? This is the torques that we're going to send to the motors over time to move the system in the way that we want the system to be moved. And as an optional thing, we can consider cost functions to minimize energy, minimize time in which we move, or maximize robustness. We can go pretty crazy over here with cost functions. But if we don't consider a cost function, if we just have the initial state, final state goal, and then we try to find any feasible trajectory, that's called solving a feasibility problem. Yeah, and for the dynamics, I should also say that you can approximate the dynamics, right? So in these slides, I will speak about the framework that I used, where I consider the full body system dynamics. So the robot is made out of different links, and we're considering the masses and inertia of every single link. But we don't need to do that. We actually, most people approximate these full body dynamics to have a system that is easier to compute and faster to solve. And you can approximate it in many different ways, with the single rigid body dynamics, with centroidal dynamics. There's many different models. If you listen to the talks from people from Boston Dynamics, they use called the potato model, where basically they take a given configuration, and instead of reasoning on the individual inertias and masses of each link, they assume that, okay, for this configuration, if my mechanism was not articulated, if it was a rigid body, then you can approximate it as a potato and consider just the dynamics of this single rigid body. Yeah. Okay, so you can approximate dynamics to different degrees of fidelity, and you can also solve the optimization problem in different ways. You can use DDP, you can use direct transcription, and you can use different methods. I'll be talking about direct transcription again because this is the method that I like the most in terms of its simplicity and ease of use, ease of explaining, and also easy to implement. So in direct transcription, if you consider this plot for a second, the horizontal axis represents time, and the vertical axis represents x. So remember, x is actually a multi-dimensional axis because x is the state of our robot. So it's just a bit conceptual graph. Don't take it as a 2D graph. The way direct transcription works is we first segment time. So this is when we convert the continuous problem into a discrete problem. We segment it into different slices. And then for each slice, what we're going to do is we're going to discretize the joint positions and the joint velocities of the system. Those are the blue dots. So basically here, if we're going to have 100 points, if we're going to have a trajectory that has 100 points, we are going to have a huge vector where we have the joint positions and joint velocities for each of these points in time. Okay?
How do you generate those?
I'm sorry?
How do you generate these points?
I think he's optimizing over them.
They can be the initial
basically
points.
saying that everyone is discrete, right? Yeah, it's a discrete set of position for every one of the, let's say the degrees of freedom.
No. It's the discretization is in time, not in value.
Is it only in time or is it also the positions of the various?
No. So these are the decision variables to our optimization problem, to the numerical optimization problem, and we're going to discretize time, but each of these dots is basically a vector with the numerical values for each joint position and each joint velocity in time. Okay.
But those variables are still continuous. They are continuous.
Yeah, the joint values themselves are continuous. The discretization is in time, not on the joint values or the position or velocities. And if I got it right, the question was, okay, this is a numerical optimization problem. It needs an initial value for a guess. What are those values? And the answer is they can be random. They can be random. They can be all zeros. Or if you know that the robot, for example, for a walking robot, it has a nominal configuration, you can just use that nominal configuration repeated for each point in time.
Yeah.
So here in the plot, they are somewhat random. And besides discretizing the joint positions and velocities in time, we're also going to discretize the torques that we are commanding to the motors throughout each of the slices. And if the robot has to reason about contact forces, for example, a walking robot needs to reason about the forces that it experiences at the feet, then we also discretize those variables. But again, only in time, not in their numerical values. And as you can see, we will, when we start with an initial guess, it will be somewhat random and it doesn't make sense. It's not continuous in the state space of the robot. There are these gaps that are not how the system would behave in the real world. And these gaps are called the dynamics defects. Yes.
I just have one question. If you start completely random, can't you get 2 time steps where the vectors are so different that you're making like a very abrupt jump?
Yeah, which are these jumps? Like these jumps here, they could be, I mean, here they are kind of already hinting at the final shape of the curve, but they don't have to. They can be complete rubbish and lead to very large discrepancies and discrete jumps. And basically that's just plain wrong because it's not how the physics of a real system would work, right? But the reason why we're having to talk about this in the first place, and just as I was saying, these are called the dynamics defects. The only reason why we're doing this is because we're basically splitting a big trajectory into small trajectories and solving this full optimization problem where we're trying to connect these gaps. We're trying to eliminate these dynamic defects. And so these are highlighted here in red. And when we click solve on the optimization problem, when we call the numerical solver, we formulate it mathematically such that we formulate mathematical equations that we want to converge to zero. And then the numerical solver will iterate, and with each iteration, it will hopefully drive these gaps closer to zero, right? Which is what the animation here shows. And then lastly, the animation will show that you can use different levels of discretization. It just means that the more discretization, the more you discretize the problem, the more decision variables you will have. So as a benefit, you will approximate the dynamics of the system better. But as a disadvantage, you're clogging the numerical optimizer with all these decision variables and constraints. And basically you're increasing the size of the numerical problem, making it more difficult and time consuming to solve. Okay, so in summary, for the direct transcription, you divide the trajectory into n equally spaced segments, and then the joint positions, velocities, torques, and contact forces are the decision variables. These are the numbers that we're trying to find that constitute the trajectory that we want to get so that we can send it to the controller of the robot, right? So it knows how to move the motors. And the constraints that we are going to follow, that we are going to formulate, are the system dynamics. And here again, you can approximate the full body dynamics, but we're going to use full body dynamics for this case. And if it's a walking robot, or you're doing manipulation, you might want to also constrain the contact forces to lie within friction cones. And then finally, you can also formulate the task requirements themselves as constraints. So if you want the feet or the hand to be somewhere in space, you would formulate those as constraints to the problem.
So there is an interesting thing here, is that you're at the same time specifying the joint position and the velocities and the torques, but is there any redundancy there? So are you not, if you define the last three, for instance, are you not defining automatically what the joint positions are going to be, and vice versa?
Yes, that's a very good observation. So in this approach, we have a redundant representation, right? When we go back here to this to this initial plot, and I will bring this up again when we go into detail about the dynamic defects. When we are, for example, at this blue point, we know this position because we're discretizing the joint positions and velocities, and we also have the torques, right? And so we have the evolution of the system for that time slice. So we can fully describe that. But then when we reach here, we have yet another set of decision variables that also specifies what the system state is at that time. So we have a redundant representation of the system. And so part of the job of eliminating these gaps is saying that, okay, we have a redundant representation, but we need to make sure that it's going to be consistent in its final form.
Right. And so you must have a reason to do that, right? And reasoning in that redundant representation. So what is the reason that you chose that, right?
Yes.
You see what I mean? So as an optimizer, I would say what I'm really interested are the position of the joint. And I just want to make sure that there is a feasible path from one joint to another. That's what I would say as an optimizer, right? And so, but you are solving the two things at the same time. So what is the big advantage of doing that?
This is awesome. This is an awesome question, because this highlights one of the big advantages of direct transcription over other methods. So if we don't use a redundant representation, like other methods do, you don't have to define additional constraints to eliminate these gaps, right? Because you have like a continuous evolution of the system over time, because your representation of the decision variables does not allow for otherwise.
Yeah.
But so what is the advantage in doing this? Well, the advantage is that if you discretize the state a long time in this way, formulating constraints on points in time in the middle of the trajectory, in arbitrary points in the middle of the trajectory, becomes trivial for the numerical solver. So say that I want to pick this point here in the middle of the trajectory, and I want to formulate that all torques must be within bounds. Well, this one maybe is not a good example because you could do it also on the other ones, but maybe for this point in time, you want to constrain the kinematic configuration of the robot such that the hand is in a specific point, or you want to hard code the configuration of the robot. Because we have the decision variables for this state of the robot in this specific point in time, these become simple equality or inequality constraints on decision variables. They are not a function. And so they become very amenable for numerical optimization. It becomes very easy. Because think about it the other way around. So if we don't do this, say we have the initial state of the robot, and what we're going to discretize are only the torques that we are going to apply over time, right? We don't discretize the joint positions or the joint velocities. This would give us a continuous representation. But then if I want to formulate a constraint for the joint positions or the Cartesian position of a point of the robot in the middle of the trajectory, first I will need to integrate all of the torques to propagate the initial configuration, and only then apply the constraint. But this becomes so complicated, and then the Jacobian to get the derivatives of that constraint for the numerical optimizer are going to be a lot more complicated.
Can I build on that question? I had prepared a specific, very similar question that he asked, and you describe this dynamics using a function that you might call like an external package to calculate that how the system evolves in that time step, right? Mm-hmm. And you're gonna feed it the variables of your problem, right? So that it can calculate how the system will evolve. And then what I'm saying this having already looked at your package, and you have these two methods, which I'm sure you're gonna talk about them, right? The forward defects and the backward defects, which kind of like hint at the problem that Pascal was talking about of this redundancy is kind of you choosing what is the redundant variable that you want to pay attention on, right? And do you enforce, so when you have the defects there, do you represent them as variables, the defect itself, and you try to minimize them on the objective function? Or do you have an equality constraint that implicitly your solver is trying to arrive at zero, right?
Yes, the second one. So
the second one.
The size of the gaps are not decision variables. They are calculated as part of the function evaluation for the constraint. And then that value is the one that is being used in a linear equality set to zero. So you're basically calculating that on each iteration of the numerical solver, one of the constraints is calculate that gap for all the gaps, and then the goal is make it zero.
So you have the equality constraint that itself you input the f that is maybe an external function that you're calling that. Yes. The inputs are going to be all the other variables, right? Which I yes. think you're going to arrive at this point at some point, but
yeah, I didn't plan to talk about forward versus inverse dynamics, but I will in the next slides talk about the dynamics defects themselves, like what basically we already covered a lot of it, but I have a few slides on this. So yeah, this animation and the videos that follow are just showing the results that you can get from solving this kind of problems. So here is the 3D visualization of the animal quadruped, where you can see in yellow the contact forces, and the green lines are the paths of the feet in space. And then you can see the execution on the real robot. And then on this video here, you can see the Talos humanoid robot. And again, now, because it's not the contacts between the feet and the world cannot be simplified to a single contact point. Another way to approximate it is to consider only the vertices of each of the foot. So if we consider that each foot is like a rectangular patch, we can have 4 corners of that rectangle on each foot. And then those are the 4 yellow arrows that you can see here, the contact forces on those points. And here the goal, well, the goal of the robot is to jump, but the robot doesn't know that it needs to jump. Actually, I want to describe a bit better what the constraints are in this situation. So the way I formulate this problem for this humanoid are the constraints for the system dynamics, right? That's a given. We want to get a trajectory that is compatible with the physical behavior of the system. And then the constraints that I had were the position for the feet. Well, if we split time in 3 portions, the feet are constrained in the beginning and the feet are constrained at the end, but not in between. So the position of the feet are able to move in the middle. And then I also have constraints about the contact forces that the feet can experience in these 3 segments. So at the beginning and at the end, the feet are capable of experiencing forces, but in the middle, they must not experience any external force. And as you can imagine, this is like very different from telling the robot to jump. And actually, the initial guess to this problem was the robot standing in a very different configuration from this, where the arms were straight pointing down. But the result that you obtain, the emerging behavior you get from this kind of trajectory optimization formulations that reason about the whole body dynamics of the robot, you can see that it has chosen to start with the arms in this kind of position, and then actually use the arms to build up momentum to lift the feet off the ground. Well, it's just doing a jump, but we never told the robot to do a jump. We just told it that, okay, there's a point in the middle of the trajectory. There's a few fractions of a second in the middle of this trajectory where you can move the feet, but the feet must not be in contact. And so the robot figures out that, okay, given the whole body dynamics that I'm aware of from our model, I have no other option but to jump upwards because it cannot go down. Yeah, and some people usually laugh at how small this jump is. And I actually had to lower the camera to the floor to show that the feet were coming off the ground. But this robot specifically is very different from, for example, Atlas from Boston Dynamics, or even the new Unitrees, even though this is electric also, and Unitrees are also electric. The bandwidth of the torque control of these motors is quite limited, and it's a heavy robot. So this is actually quite an impressive feat for this specific hardware. And again, the emerging behavior of the arms swinging up is really interesting to see emerging from the optimization.
Just one question. What if it was too heavy? What if it was like an infeasible optimization problem?
Yeah, it will. The numerical optimizer will not converge and will output an error code. It will say, okay, I get what you're asking me to do. I get that you're trying for my feet to stay still at the beginning and at the end, and they can move in the middle, and I cannot experience contact forces. But the numerical solver will try as hard as it can, and it will say, actually, there is no way that I can satisfy your dynamics constraints, because given the weight of the robot, there's no way that I can produce enough torque to lift the feet off the ground to produce 0 forces.
Thank you.
As a kind of follow-up to that, what if the robot does have enough torque, but like in your example before about lifting the bucket, what if it had like a really heavy backpack on that it didn't know about? And so the solver converged that says you can jump, but then it tries to jump and it can't.
Yes, that's a good question. So the robot will fail, basically. So because you calculate a trajectory, you send that trajectory to the robot, but then the controller that is trying to track that trajectory to make sure that the execution on the real hardware is as faithful as possible to what you had planned, given your model, it just does not add up, right? It's almost like, well, I don't think it's the correct thing to say here, sim to real gap, but it's almost like that, right? Because in your simulated environment where you were solving the optimization problem, you were taking into account a model, and then in reality, you have too big of a gap because the model is too different. And so there are multiple ways of doing, trying to address this issue. So you could, as you're executing, continuously collect information from the robot and understand that you're deviating too much, and basically realize that, oh, the model of the real robot is very different from the model that I used for optimizing. That's the only way it explains that it's deviating so much because of the external disturbance. You can still get around some of these if you're constantly solving the optimization problem as you're executing, which I'm not doing here. And basically, if you do that, you're solving what people call a model predictive controller problem, right? MPC. Because as you're executing, you're continuously replanning, given the newest information you've got from the state of the robot, taking that as your initial state and optimizing from there. And so even if you're deviating, you can be robust to changes. But it only goes as far, right, as it can. So if you have a super heavy backpack, it doesn't matter if you're using MPC. If the robot if it's simply beyond the capabilities of the robot hardware, then it will not be able to transport or carry that huge, very heavy backpack.
I see. Do people try to optimize like with that kind of feedback in the optimization? Like as part of your dynamics, have the PD loop or some version of that?
Yeah, so there are some, if I understood the question correctly, there are some formulations where you have basically parameters that are flexible, parameters of your model that are flexible. So say that you know that the robot will be wearing a backpack, but you don't know how heavy the contents of the backpack are. So instead of assuming that you have a static model of the robot, and I don't mean static as in not moving, not articulated, but static as in the robot weight of the different parts of the robot remains the same. So instead of assuming that, you could have an extra parameter that says, okay, this is going to be a dynamic parameter of the model of the robot, and we're going to do online parameter estimation of how heavy the backpack is. And by doing so, as you're collecting data from running the real robot, the more data you collect, the more you are able to correctly pinpoint how much weight is in the backpack and what are the mass matrix of that. So for example, if the weight is all focused on the bottom of the backpack, or if it's just on the top of the backpack. And by doing so, the better the closer you are to estimate the parameters of the backpack correctly, then the better, right? Because the model that you're using for solving the trajectory optimization problem becomes more accurate. And so the trajectory that you get as a reference for the controller to track is higher quality and more faithful to the real system.
Nice. Yeah, so something I work on a lot is parametric optimization. So I was kind of hoping for that answer. I'm definitely going to look at that body of work.
Yeah. Okay, let me just have a look at the time. Okay. So the dynamics defects, I think we've covered most of it, but let's zoom in on one of them and understand in detail what's happening here. Basically in blue here on the first dot in time k, we have two times, right? Two adjacent points in time that we have discretized, tk and tk plus 1. And for both of these points, we know we have discretized the joint positions, the joint velocities, and also the joint torques and the lambdas, even though I'm not showing them for this point here because they are not relevant to how the system propagates in between these 2 points in time. They're also present here, but let's not consider them right now. And again, this goes back to the redundant representation that is used for the decision variables of this problem, because from this point, with these positions and velocities, I also have the discretized torques and contact forces. So I'm able to almost run like a tiny simulation to propagate the state of the robot over time. And I will end up in this red diamond here, which might or might not be coinciding with the state of the robot at that point that we discretized as well. And so this is again, the problem of this approach to discretize the problem is the redundancy and the mismatches that might happen. And so we must formulate this red line here, like how big is the gap? We must numerically calculate it and formulate it as an explicit constraint for the solver to drive to zero. Yeah, and I don't have it here, but what Andrew was talking about, the forward versus inverse dynamics, is that in order to calculate this line, or in order to enforce the consistency required by this redundant representation, there are two approaches that we can use. We can use the forward dynamics of the system or the inverse dynamics of the system. So just quickly, this one that I spoke about using the torques to integrate the state of the system, almost like a tiny simulation, that is forward dynamics, right? Forward dynamics gives us the joint accelerations that we can integrate over time, given the state of the robot and the controls that we apply to the robot. But we could also formulate these constraints with inverse dynamics. And how would it work? Well, we have the current state here, we have the previous state here, and we have the discretized torques. So we know from the previous state and the current state how the robot should move, right? So we know the desired joint accelerations in order to transition from this state to this state. And so the inverse dynamics problem, what it solves is, given the known joint accelerations, what are the required torques to produce it, right? And when we solve those, then the constraints become, okay, the required torques that we obtain from the inverse dynamics must be the same as the ones that are formulated from this decision variable discretization. And that then becomes a different constraint for the solver. Those are two different approaches. And actually inverse dynamics is better because it's faster to calculate. And so if you can imagine that when you go back to a problem with hundreds of points, calculating this over hundreds of points at every iteration of the numerical solving, it becomes important how quick you can calculate each of those constraints. So if inverse dynamics does it faster than forward dynamics, then you should use it. There's other advantages, but I think we can skip them for this presentation today.
But why is the inverse dynamics faster than the forward dynamics?
Yeah, there's a few reasons. The most important one is that it doesn't need to perform a matrix inversion of the mass matrix of the robot, and doing that inversion on the forward dynamics is more expensive numerically to calculate.
Fundamentally, that's the same thing, right? So that's going forward and backwards. You should get it's like the inverse of it. And that's why because you don't have to have this inverse, you cancel the inverse and it's more efficient. That's what you're saying.
Yeah.
See, that's interesting.
Yeah, and there's other things that I also observed when I used inverse dynamics that I could not explain, which is if we use less points in time to discretize the problem, the trajectories that we get with inverse dynamics are more faithful than if you were using forward dynamics. So I did a few experiments, empirical experiments, where I discretized time with a high number of points, and then I solved the same problem with each time with less and less points. And I compared the output trajectory from forward dynamics versus forward dynamics with the original baseline that used a lot of discretized points. And I observed that the forward dynamics version was deviating more quickly from this baseline than the inverse dynamics. And
that's purely numerical. That's purely because of the numerical results.
So I didn't explore this. So to me, it was not completely intuitive why. And yes, you're right. At the time, I could not rule out numerical artifacts. But a colleague of mine, I have a mention of his lab in one of the final slides. I think he actually did some research on this behavior after this, and he explained why. But to be honest, I don't know why. I haven't checked.
One thing, just an anecdote on this, on the inversion thing, where I like to think of is F equals MA. If you want to know F and you know A, then you just multiply. But if you want to know A from F, you have to invert the M matrix to
That's
get
that's what I understood. It's interesting, actually.
And do you imagine that? Did you check the errors that come from inverting the matrix itself?
That's what I was saying.
No. I think this is where my knowledge gets yeah, I didn't do this. And I think this is one of the other advantages of discretizing the whole problem, is that you can then use inverse dynamics, because you wouldn't be able to use inverse dynamics, or at least I can't think of a way how you would formulate the gap constraints without discretizing all the states across time. Right, because if you have a single state at the initial point and then the torques over time, you would have to use forward dynamics to simulate the evolution of that initial state across time. Okay. I will pause the presentation and I will go over here. I think this should be working. Here is just a Jupyter Lab. I gave a similar presentation in a Julia conference in Boston. I think it was in 2023. And so I showed actually the presentation itself was quite similar to this one, but we didn't obviously go into so much technical detail, especially because it was not the crowd was not entirely from robotics background. But here what I have on the left is a Jupyter notebook, and on the right, a 3D visualization of a robot arm. This is the Franca Panda. And just to show you how the framework works, and this one is open source, you can try it out. We create a robot. Is the zoom on the left notebook enough? Can you see it clearly? No. Or should I increase it a bit?
You can make it a little bit bigger. I think it would be nicer.
Like that?
Yeah.
Okay. Let me see if I can. All right. So we create a robot. This is basically just spawning the kinematics and the model. And then we create a problem. This is a high-level description of the optimization problem. And I'm just saying I want to use 201 points. So this is the time discretization. And then this is the space between the duration between each pair of consecutive points. So basically 1/100 means that we are going to discretize this trajectory at 100 hertz. So we can actually print the problem information here. And so with 201 knots at 100 hertz, we are representing 2 seconds of trajectory. And then what I have here is that I want to I want to modify the problem, right? This is what this function is doing. And in Julia, the reason why this exclamation mark is here is meaning that we are modifying, mutating the first parameter that we pass it. And so I'm trying to fix the joint velocities for this optimization problem, fix the joint velocities of the robot, and then this one means the first point of the trajectory. And this number of knots is the last point of the trajectory because it's the total number of knots. And then the final argument is the values, the specific numerical values that I want to constrain it to. So intuitively, in plain English, what this means is we're constraining the initial and final joint velocities of the robot to 0. The robot starts at a standstill and finishes at a standstill. Then in the next block, there's this auxiliary function that is a cubic times scaling. It's just a cubic polynomial. And we're then using a for loop to define a target position for the end effector of the robot. And you can see we're just using cosine and sine here on the y and z. So this is a 3-element vector, x, y, z. We're using cosine and sine on the y and z. And basically what we're doing is asking the robot if it can draw this yellow circle. That's the target for the end effector.
Sorry, can you re-explain the cubic time scaling?
Yeah, so the cubic time scaling is just a way of formulating parameterizing time. So when we're using this cosine and sine for the circle, we're using the cubic time scaling to formulate the target of the end effector so that it accelerates at the beginning and then decelerates when it's reaching the end. Otherwise, if we just use equally spaced targets in time, it will try to instantaneously accelerate, right? To reach a constant acceleration for drawing the circle, which it makes the problem very difficult because it's not how you would solve it physically.
But you are actually cheating when you do that, right?
We are kind of embedding some knowledge of the task into the constraints of the problem, yes. But what we could do is, instead of using this cubic polynomial, we could formulate the equally spaced in time, the targets equally spaced in time. We know that this is not feasible for the robot to do because it cannot start at a standstill and immediately achieve positive velocity to track that constant trajectory in Cartesian space. But the solver would still converge to something. It would converge to something that
It's as close as possible to that.
Yeah, as close as possible to that. And then you can try to track that on the real robot.
That's very interesting.
Do people ever model that kind of, because it's basically a safety constraint, or it's sort of a safety constraint, right? You don't want your robot to like fling over to the final state. Do people model that more like explicitly?
Yes, there's different approaches to this. You can model it explicitly at the planning level. So introducing safety checks to monitor how you're planning and make sure that the plan is feasible and is not doing something unreasonable. But in these kind of things, you want to introduce safety checks at different layers of the system, right? You wouldn't want to just have safety layer on the planning level. And so on the controller level, when you receive these reference trajectories, I would argue that you should make the assumption that whoever gave you this trajectory might make a mistake. And so you could have a watchdog or like monitoring the incoming reference to see, okay, are the joint velocities that this reference is trying to achieve, are they reasonable or are they trying to drive the robot crazy? And by having these safety checks spread across the different layers of the system, then you are better protected from human error or from algorithms not being able to solve the problem. Okay, so in the next cell, what we're doing here, this initial queue, if I execute it, I'm rendering the robot with that initial queue, which is 0 position on the first joint, second joint, and third joint, then minus 90 degree on the third joint, which is the elbow, and then just rotating this joint here so that the end effector points like that. So this is our initial guess to this task, but you can see that the end effector is not even coinciding with the circular path that we want to draw in. And that's what I meant when we have like an initial guess that does not need to be super good. If it could be rubbish actually, and solvers can still find a way to reach a a feasible solution. But of course, the closer you are, or the better your initial guess is, then the numerical values that you use for the decision variables are closer to something that makes sense. And so the solver will have to do less work. It will converge faster. Happy days.
So is that just what you think IPOpt as like the start, like as the first or the 0th iteration?
Yeah, the initial
So it
value
doesn't
problem.
appear in the model itself, right? Like
Yeah.
besides.
So these lines are just setting the configuration of this mechanism, but are not changing the problem. Here, initial queues, I'm going to repeat the initial configuration over time. So even though we want the robot to draw a circle, our initial guess is the robot standing still in this configuration. The initial joint velocity guesses are zeros, and the initial torques are also 0. Then we concatenate all of that, and basically this huge vector is, first, they are the decision variables of the problem, and the specific numerical values that are here are the initial guess of the problem. So if I take this semicolon out, we can actually print it. And you can see that for such a simple problem, 2-second problem with 200 points, 201, we have 4,214 decision variables. And then we just like formulate it numerically. And here I'm using IPOpt with the default linear solver and with the default options, I think, yes, with the default options. And so this is the worst it could perform. If you change the linear solver to something better, and if you change the options to tune it a bit, it will be much quicker. But if I solve it there, I just solved it. Well, we can see a bunch of information that is very interesting, but if I scroll down, it says exit optimal solution found. It shows the total of seconds spent in the optimization problem. So it took 0.2 seconds for a 2-second trajectory, discretized at 100 Hertz. And then we can see more details of the solution process. So we can see that the solver took 9 iterations, and we can see that the error is decreasing a lot as we iterate. So the infeasible primer and the indefeasible dual variables of the problem. And, like there's no point in solving a numerical optimization problem to this degree of numerical error. Like to the power of minus 15 is just, there's no need to solve it to that amount. So if you tune the options and say, okay, I'm happy with something like -3 or -2, because anyway, there's going to be errors. Anyway, when we send this trajectory to the robot, the controller is going to be trying to track it as best as it can, but is not going to be tracking it perfectly, and there's always some errors. So solving for 4 iterations in this case would be completely feasible to send it to the robot and watch it work. Yeah, and so we can see here, we solved it, and now if I play it, we can see the robot drawing that circle in 2 seconds. And you can see the nice behavior. It's not like some approaches where you just call inverse kinematics and then you have a very robotical behavior where the robot body is very static. Here you can see very fluid motion where the robot draws the shape neatly. And yeah, it looks pretty cool.
So how do you achieve the fluid motion instead of something which is more static?
From the dynamics. So because it knows the dynamics of the robot, the trajectory that it comes up with is trying to respect those dynamics. So if I was to solve the same problem, okay, I don't have it ready here, but there's or maybe I have it ready. Wait, let me check.
I'm simulating what I would do, and I can be very static or very dynamic.
Yeah.
And I have that, as a human, I have that option. So does the robot have the same option as I have? I can be very static and draw a circle, or I can be, wow, using my knees and so on.
Yeah.
So is the robot, yeah, go ahead.
You can definitely modulate or influence the output behavior by having a cost function where you can describe that. For example, by minimizing energy, or for example, if you just sum up all the joint velocities of the trajectory and add that, and this is your cost function, you basically want to minimize joint velocities, then it will be quite stiff because it's trying to do the motion that it needs, moving as little as it can. So you could definitely modulate these behaviors.
I noticed the objective is 0 for all the iterations. Do you not have an objective? It's just the feasibility?
Yeah, in this case, it's just like find a feasible solution. And it will find the one that is closest to the initial problem. But I think there's an option to, I need to check the code. I haven't used this in a long time. Where is the solve with IPOpt? Here, there should be, yeah, for example, minimize torques. I think if I pass that here, now you will see values on the objective value. And you can see that the first value is 0. Why is that? Because the initial torques that we formulated as the initial guess are all zeros. So it's adding them all up. And then they start increasing. Why? Because it figures out from the dynamics constraints, in order to make the robot move, it needs to use torques. But then we are trying to minimize torques as a cost function. So there's like conflicting things at play here with different interests. You want to use torques to move the robot, but there's a cost function saying, okay, try to use as little torques as possible. And so this one takes a lot longer to solve, as you can see, because, and again, you can tune the options to not have this happen, because you don't want the solver to take these many iterations to solve it. Say, like, if we look at the behavior, here we start with 0, then we go to the power of 1, power of 2, and then in the power of 2, we start with 5, and then we decrease from 4 to 3. And then look, from iteration 21 beyond, we're always like at 3.11, 3.11, and we're basically getting diminishing returns. So basically, the solver is trying again to minimize this cost function as best as it can, but there's very little gain in doing so for so many iterations. So you could cut it short here, where you have already a feasibility error of power of -2, power -3, and you reached a pretty good like plateau on the cost function. And
Yeah,
if I play
sense.
this now, if I play well, did it find a solution? Yeah, it says solve to acceptable level. If I play the solution now, it will look different. So you'll see that the robot is now a lot more straight, to probably cancel out the gravity effect on the joints at the closer to the base. So it's trying to save some torque there. And then where it folds is closer to the wrist, because beyond the wrist, the linkages of the robot are lighter. And so it doesn't require so much torque to be able to move it around. And so that's why you get this kind of behavior.
Does this have the defects control? Because that's why I initially asked. I thought that was going to be in the objective, is minimizing the defects.
Those are hard constraints.
Oh, okay.
Yeah.
So the defects, as he was talking about, they come implicitly at the quality constraints.
Mhm.
Yeah.
Which we can draw on the board later on.
Yeah, and I will just play this one again. So this one, notice how the robot moves with the minimization of the torques. And now if I set that to false and play it again, you will see that the elbow is folding more. It's costing more torque, but we don't have that as a cost function. Anyway, moving on, you can see here in this plot the evolution of the joint positions, the evolution of the joint velocities over time, and then the optimal torques that we should send to each of the motors to execute this trajectory.
I just have one question. So this has 4,000 variables for how many degrees of freedom?
So there are 6 joints in this robot. So for each state, you would need 6 joint positions plus 6 joint velocities plus the vector of 6 joint torques that you want to send it for each point in time. And because we're using 201 knots, that should add up, right? So 201 times 18, right? Oh, It does not add up. Why is that? So wait, initial configuration. So this is 6. Oh, sorry, this is 7. This is not a 6 degree of freedom robot. The Frankie is 7. So you've got 7 positions, 7 velocities, 7 torques, right? So that's 21 times 201, and that's 4,221. And that should, yeah. It's less because here we are removing the torques from the last point, right? At the last point, we don't need the torques. And this should add up with the total number of variables here. Well, it does not. I don't know why.
Can you speak to like the scaling of this? Like once you go to the more complicated, like the Tesla humanoid one, how many DOFs are you optimizing over?
On the quadruped, so let me go back to the slides.
From what I remember, Atlas was 58 states.
Yeah.
58, yeah.
So on the quadruped, you have 12, 3 on each leg. 12 actuated joints, but then you have the floating base, which is underactuated. And so you need the position, position, XYZ, the velocity, you have the position of the base, which is the translation in space and the orientation in space, right? So you need parameterization for those two things. And then you also need to characterize the velocity, linear velocity and angular velocity of the base. So those are additional decision variables to describe the state of the robot, which are not related to directly actuated joints. And so this one, I think, is 18 plus 18 plus 12, so 18 positions for with the arm on top of the quadruped. Those would be 18 joint positions plus 18 joint velocities plus 12 joint torques, or plus 18 joint torques, and then plus 6 floating base positions plus 6 floating base velocities. So it can grow quite a lot, but it's still feasible to solve these kind of problems. And they are surprisingly fast. You can achieve amazing results with them.
Thank you.
I think I actually have a slide about this. So yeah, how do you go from this to that? So there are two differences. The quadruped has a floating base, unactuated, and there exist ground feed contact forces. And so first you need your vector of joint positions. They need to account for the position and the rotation of the base, as well as the linear and angular velocities. And then you can optimize something like this, where the robot is just floating in space, where, oh, I cannot play it. That's unfortunate. But basically, you can optimize a trajectory that reasons about floating base system. So the base of the robot does not have direct control over, because you don't have jetpacks on it. But you don't have contact with the feet. And then to add the contact with the feet, then you add extra decision variables for the contact forces. And then you also need additional constraints to say, well, if we use a Coulomb friction model, the contact forces should be lying within the inside of a friction cone or friction pyramid. Yeah, so for to go from an arm to a floating base like a quadruped or a humanoid, you do need additional details on the formulation. Okay, so that concludes the demo. It's 8:40 here in the UK. I will finish just these few slides. Okay, so some advantages and disadvantages. Here is we can have a nice discussion. So direct transcription is a powerful and effective method for optimization. Optimization with full dynamics allows interesting behaviors to emerge, such as the ones we saw when the humanoid was doing the jump and the arms were used to build up the momentum. And then disadvantages in general. Full dynamics are more expensive to compute than simplified dynamics with some sort of approximation. And this can pose challenges to MPC. So if you want to wrap this solver and call it multiple times as the robot is moving to obtain new reference trajectories for the actual state of the robot as it is running in the real world, the faster you are able to solve this problem, the faster you are able to get that new reference trajectory. And using full dynamics is a challenge because it's a lot more expensive to calculate than if you were using some other approximation. And then no model, including one with full dynamics, will be the same as the actual robot. So the actual robot changes over time. There's cables that are inside the robot that are not modeled. The motors are affected over time with wear and tear. So it doesn't matter how good of a model you have, the real robot is always going to be different. Yeah, then there's a few advantages and disadvantages of this specific framework that I was using for my PhD, but I don't think it's worth discussing them right now. I have a slide here about like the different packages that I used for this framework implementation, for the videos that I showed and the visualization. Yeah, so you can have a look at each of these packages later. Finally, so I'm also a really big fan of the Julia programming language, and it allowed me to make really big progress in my PhD, especially in solving these and formulating these very complicated numerical optimization problems. And there's other nice videos on YouTube you can go and have a look, including from people at Boston Dynamics like Robin and Tuan. And then this is the slide that I added today, just before the presentation started. So Carlos Mastali is the colleague that I mentioned earlier in the presentation, and this is the page of his research lab in Heriot-Watt University. And he's also with the IHMC in Florida, the Institute of Human Machine Cognition. I think that's what it stands for. And they have like also NASA Valkyrie humanoid robot there. They also have their own Nadia humanoid robot. They're doing pretty cool stuff. And so the reason why I'm linking his research group page here is because the work about this forward versus inverse dynamic differences, he did some follow-up work on that. And he is also actively working on very high performance MPC with numerical methods for quadrupeds and for humanoids. And so I'm no longer actively working on this from an academic perspective. So if you want to have a look at the state of the art and how people are using these methods, you can have a look at his research. And then the one on the right is so this whole talk has been about making a point that if we use full body dynamics, we get very nice trajectories that we can then use very simple controllers. So we're trading off, right? Instead of having a very complicated controller or a whole body controller with a QP problem, we can have something as simple as a PD controller. And we're trading off that complexity by bringing it to the planning stage, by accounting for a whole body dynamics, for the whole body dynamics of the robot during the trajectory optimization. But I just saw this work very recently where they said that they were exploring an approach where they're running MPC, and in the video here you can barely see it, but this green unitary go-to robot, they basically linearize the full dynamics of the they linearize the dynamics of the system on this single nominal configuration, and they use that for running convex MPC, and they show walking, and they show disturbance rejection, and they also show it on heavy humanoids. So I mean, the field is constantly evolving, and people are making a case, okay, it's nice to use whole body dynamics, or you can go crazy and just linearize the system and then run convex MPC really fast, and that is sufficient. And yeah, it's just interesting to see all of this happen. And with that, I conclude the presentation. So yeah, just I like this quote quite a lot. All models are wrong, but some are useful. and I think it's very interesting, and I really live by it. And yeah, so with that, I would like to thank you so much for your attention. It's been almost 2 hours, so I really appreciate you listening to me rambling about this, and I really appreciate all the questions as well. So I hope you had a good time and enjoyed it.
Thank you very much, Henrique.
Thank you so much.
Thank you. That was very thorough, and you passed through a lot of interesting stuff, and your practical knowledge on how you have applied those things. We have been seeing all those problems in a very theoretical point of view, and seeing the different options that you have, and the motivations that people talk about behind of them. And so it's super nice to see your actual experience and how you have done those things using the like classical solvers, using Julia in general, which that I love very much. So thank you very much. If you do have still more time and energy, we would like to ask you a few questions, if that's okay.
Yeah, I think that's okay, but maybe not too long, because I still need to go have dinner.
Yeah. I'll stop the recording as well, so that we have a clean presentation that you have done.
Okay.
And we'll continue after 1 second.